Hello, BC Calc. This is your day 127 notes, and it is the last day of new curriculum and content. We've made it. Well, we've made it in about 20-ish minutes. So let's go through today a vector summary, and we're going to recall some projectile motion applications similar to what you would have seen in pre-calc honors last year. Let's jump right into it and talk about dot product. So dot product, for our purposes, will essentially be used to determine the angle between two vectors. And we talked about this a little bit earlier in the week, but the dot product definition that we're going to wind up using to find the angle between two vectors is if I find the dot product of v and u, that would equal the magnitude of v times the magnitude of u cos theta, or maybe more simply, so that we can find angle theta directly, we can rearrange the formula such that cos theta equals the dot product divided by the magnitude of each vector. So just as a quick reference as to how do we compute an angle between two vectors given 3, 4, and 5, 12. The angle that we're looking for in question here would look something like this, right? If you could graph those vectors based on their components, we're looking to determine the measure of that angle. So the dot product, as a recall, is the product of the component pieces, and then you find their sum. So u times v as a dot product is 3 times 5 plus 4 times 12 for a total of 63. We should know at this point how to find the magnitude of each vector. Magnitude of u winds up being 5, magnitude of v winds up being 13. So that's some nice looking numbers there based on the component form of each vector. So dot product over the product of those magnitudes would be 63 over 65. And therefore, if we do cos inverse of 63 over 65, we get 0.249 radians. And although our entire focus in this course has been on radians, perhaps we might see on the very final moments here a little sneak in of some degrees here. The angle between those vectors would be approximately 14 degrees. Might even see degrees at the end of the lesson today too. So we're going crazy on day 127. So as a quick summary of what we know up until this point about vectors, we have our position vector, r of t, whose components are of the form of a pair of parametric equations, x of t and y of t. And then, of course, we can get velocity from there by finding the derivative of the position vector. So x prime of t and y prime of t would be its components. We can find the speed by finding the magnitude of the velocity vector. And I realize I'm going through this maybe a little bit quickly, so if you need to pause and make sure you have it all down, of course you may do that. Acceleration would be the derivative of velocity, or the second derivative of position. And last but not least, we have a definition for a unit vector when needed. It is the vector divided by its magnitude. And as you recall, a unit vector is a vector of length 1. Okay. So what we'll do from here is let's do another practice question with defining some vectors in terms of position, velocity, acceleration, and then we're going to talk a little bit about projectile motion at the end of the lesson as well. Okay. So on the top of the next page, we have a particle moves according to the equations x equals 3 cosine t and then y equals 2 sine t. Find a single equation in x and y for the path of the particle, and then sketch a graph of this path. Well, this, to get started, is definitely an application of parametrics, right? We have x is a function of t, y is a function of t. So we want to figure out, well, what equation relates x and y by eliminating that parameter t? Well, you've done examples like this before where we eliminate the parameter t, and it really comes from remembering the Pythagorean identity that cosine squared plus sine squared is 1. So if we know that identity, well, cosine of t would be x over 3 and sine of t would be y over 2. So x over 3 squared would become x squared over 9 plus sine squared would be y squared over 4, right? Y over 2 squared. And that would equal 1. Hopefully this is standing out to you as the equation of an ellipse centered at the origin, whose major axis has a length of 3, and the minor axis, which is vertical, has a length of 2. Total length of 4. Okay. So we get something that looks like this. Now, when I sketched it, by the way, that's not necessarily the direction that the particle, or the path of where it starts, I should say, but So when I sketch a graph of this path, where are we actually starting? Well, at time equals 0, the position would be, this would be 3, and the y value would be 0. So it does start here. And then as you rotate around, it's going to want to rotating in a counterclockwise direction. So that is what the path of the particle would look like. All right, so that part wasn't so bad. And part B, find V of t, A of t, and show that A of t equals negative R of t for all values of t. So if we define this in terms of the position vector valued function R of t would simply have the components 3 cosine t and 2 sine t. Okay, so from there we can pretty easily establish what the velocity vector is. That would be negative 3 sine t. This would be 2 cosine t for the y component. And then quickly the acceleration vector here would be negative 3 cosine t in this step, and this would be negative 2 sine t. And we can now quickly observe that the acceleration vector is the negated form of the position vector. So without doing much there, we can say, okay, well, therefore, A of t is in fact equal to the negated form of R of t. Okay. All right, I do want you to try part C and D. So try this piece where all you're going to be doing is taking those 3 vectors from part B, evaluating at t equals pi over 6 and t equals pi. You can sketch them on the graph above. And then part D says find the speed and magnitude of the acceleration at those values of t as well. Okay, so speed, we know how to do also magnitude of acceleration, so 2 separate computations for each of these times. Go ahead and see if you can try this part as well. I'm going to do the last part with you, though. For part E, it says when is the speed a max and when is the speed a min? So we know speed is going to be magnitude of velocity. So if I go up to the velocity vector up here and I take the square root of this component squared plus this component squared, you're going to get the square root of 9 sine squared plus 4 cosine squared. And to establish when this is at a max and when it's at a min, I'm going to do sort of a quick substitution here that I think will be to our advantage. This might not be something that we think of right away, but it will help us to easily determine where this is at a max and where this is at a min. I'm going to break up the 9 sine squared into 5 sine squared plus 4 sine squared. And once I make that break here, this definitely has a sum of 9 sine squared. I hope that makes sense because what I want to now do is combine it with the 4 cosine squared at the end. If sine squared plus cosine squared is 1, well, then this total would be just 4. So this is equivalent to what we had for the speed up here. It's saying 5 sine squared plus 4 under the radical. And having just one trig function under the radical will make our job easier in determining where this is at a max and where it's at a min. So to find where it's at a max, we can maximize this expression by saying, well, where is sine at its max value? Okay, so sine of t would be at a max at, how about t equals pi over 2? Right, if we think about the sine curve or the unit circle. And because it's sine squared, where sine is -1, squaring the -1 is also going to produce a max, and that would be at 3 pi over 2. Okay, so the speed is at a max at these 2 angular values for t. And meanwhile, it would be at a min where sine is equal to 0. Sine is equal to 0 at time equals 0, at time equals pi. So we've got these values for where we're at a max, these values for where we're at a min. And just as a quick reference, what that would look like on the ellipse is if this is 3, -3, 2, and -2. Okay. If we were to draw the speed at time equals 0, we know that the velocity is slow in this direction. But then at pi over 2, when it's heading in this direction, the velocity vector would be going fast. Okay, this is when it's at its max speed. Whereas then I rotate around to this part of the ellipse and the velocity vector here would be going slower again at pi. And then when we're traveling in this direction at 3 pi over 2, this is going fast at that point. So that's all that's establishing in part E is speed at a max or min. Hopefully that quick little substitution made sense so we can get it down to one trig function. And then analyzing where that sign is at a max and a min helps us to know where the particle's traveling around. It's not always going the same speed, of course. Okay, it's going faster at these endpoints of the minor axis, slower when we round out to the endpoints of the major axis. Okay, we'll go over part C and D next time we're together. Let's take a look at the next page, which just has some information about projectile motion. You've probably seen images very similar to this before, whether it be in pre-calc honors, physics, or otherwise. So we have this horizontal range defined on the x-axis. This would be the height above the ground for a projectile that has an initial position on the ground. It doesn't have to be at the ground level that we're launching it from. But we can come up with the components of our vectors by saying that in general, cosine of alpha would be adjacent over hypotenuse, so x over v sub 0, which means that x is equal to v sub 0 cos alpha. And t seconds after its launch, if I multiply that component by t, we can get the position at any time. Similarly, in a projectile motion application, we would have the y component as the initial velocity times sine of alpha, okay, where alpha is that launch angle there, t, minus 1/2 gt squared, which is the effect of gravity. And with the effect of gravity in English units being negative 32, we get that this is going to become negative 16 t squared at that point. Okay, negative 16 t squared is always the constant that you'll subtract for the effect of gravity, plus s sub 0. S sub 0 could represent some initial height. Okay, so if we're launching not from the ground, but from some initial height, we need that to be included with the y component as well. So here's what it looks like in terms of the basis vectors I and j, and then here's what it looks like probably in our more familiar and comfortable notation using triangular braces for the x component, the y component, in addition to having gravity and potentially some initial height. So BC Calc, we're about to do our last example of new information here on day 127. And you know what? Why not go out with a bang? Here we go. We're going to fire a cannon in our last example, right? Go out with a bang. Get that there? Okay, good. All right, so we are going to take a look at a shell fired from a cannon has a muzzle speed of 800 feet per second. The barrel makes an angle of 45 degrees level with the ground. There's degrees all of a sudden sneaking in the final moments here. Find the vector equation of the shell's trajectory. Okay, so we have, since it's being launched from the angle makes a 45 degree angle with the ground, we're going to have that this is the path that the cannonball takes with some initial velocity. Okay, so the initial velocity is 800 feet per second, and the initial angle alpha is 45 degrees. So to figure out the component form, the vector equation for the position at any given time t, what we want to be able to do is determine the x and y components based on that initial velocity and this initial angle of elevation here. Okay, so here's my initial velocity of 800. Here's my angle of 45 degrees. So we know that the x component would be 800 cos 45. The y component would be 800 sine 45. And because it's such a nice angle and we have exact values for sine and cos 45, this would wind up being 400 radical 2, and so would this leg as well. So based on that setup, we know that the position vector at any given time, r of t, would equal 400 radical 2 t. And then the y component would also be 400 radical 2 t, but minus 16 t squared for the effect of gravity. Okay. So in order to find how high the shell rises, we want to find the height when this is at a maximum. So to use calculus in order to do that, because this is something you would have done in pre-calc honors last year as well, we want to figure out, well, when is the slope of the tangent line equal to 0? So we can find dy dt here and figure out when does that equal 0. Well, it's going to equal 0 when the top equals 0. Okay, so dy dt in this case is going to be The derivative of this y component, 400 radical 2 minus 32t. Okay, if we set that equal to 0, we can quickly isolate t and get that t equals 400 radical 2 over 32. And if you want to reduce this a little bit, the time that it takes is 25 halves radical 2. So based on the fact that this is how much time it takes for us to get to where we're at a horizontal tangent line, we now want to plug that into the y component of the position vector to figure out how high the shell rises. Okay. So if I plug that into the y value up there, we get 400 radical 2 times 25 halves radical 2. And then minus 16 times, am I going to fit this in here? I hope so. All right, 25 halves radical 2 squared. Okay. All right, enter that into your calculator. Confirm that in the end that the height that the shell rises is 5,000 feet. Okay, so double check me on that one. All right, well, similarly then, can we use the same type of information to figure out how far does the shell travel horizontally? Okay. Well, because of the parabolic nature of this path, we know that it took 25 radical 2 over 2 seconds to get to this point right here at the max height. So if I double that, that's going to give me the time that it takes to hit the ground. So for this part C, it's going to hit the ground at 2 times that time from part B, so 25 radical 2 over 2, which then would just simplify to a time of 25 radical 2 seconds. So if that's how much time it takes, we want to make sure that we plug this into the horizontal distance traveled, which is the x component. So finally, 400 radical 2 times 25 radical 2. And the horizontal distance traveled by this cannonball is going to be 20,000 feet. Okay. And last but not least, what is the speed of the shell when it hits the ground? Okay. So we know the time when it hits the ground. So to figure out the speed at that time, it's going to be the magnitude of the velocity at 25 radical 2. Okay. So first and foremost, we have to just quickly define what the velocity vector is. The velocity vector v of t would be 400 radical 2. And we have the y component from part B, 400 radical 2 minus 32t. All right, and if you plug in 25 radical 2 at this point for t, v of 25 radical t, well, the x component's not going to change. That's going to stay 400 radical 2. And as it turns out, if you plug in 25 radical 2 here, this becomes negative 800 radical 2 for a total of negative 400 radical 2 for the y component. And therefore, the magnitude at that time to get the speed would be the square root of 400 radical 2 squared plus another negative 400 radical 2 squared. And if you type that in, you wind up getting that the speed is 800 feet per second. Okay. Well, BC Calc, that is it. That is our last and final example that we will be completing as new notes. So now, of course, it is up to you to go forth, study, prepare, get ready for this AP exam in just a few weeks. Of course, I'm here to help you do that, but I will always encourage you to have a great rest of your day and let me know if there's anything else I can do to help. Have a good one.